Anyone? It's okay always. It's okay if you're wrong. Why do you think that these two are in the same chapter? Always. In algebra, in calculus, in pre-calculus, everywhere they go together.
I'm guessing because
oh, you can go ahead.
Logs are linked to exponentials.
Okay, how? Anyone?
Aren't logarithms also another way of rewriting exponents?
Correct.
In a few cases as well.
Good. Any other reason? All good? Any other reason?
Is one the inverse of the other?
Yes! That's why they're here. Look. 10 to the x and log. E to the x and ln. Okay? One will undo the effect of the other. This will undo the effect of this. This will undo the effect of this. Same thing here. Thank you. Thank you. They are inverses of each other. So if they're inverses of each other, immediately we have to remember that if a function is defined, this is how we write it, on, this is domain, and this is range. So if a function is defined on A, which is domain, taking values, so the x is here, y is here, range. Can anyone tell us the inverse function is defined where?
Would it be B to
Absolutely. Thank you very much. So this is the one concept about inverse functions. Now we're going to graph both. They have two shapes, right? So let's take a look. The exponential looks like this. F of x equals a base to power x. Base is limited. What do I mean by limited? What do I mean by limited? The base can only be a number greater than 1, not 1, or it can be as a positive number between 0 and 1, not 1 and not 0, in order to define the exponential function. And you can say why. Why can't I take a 0 to the third power? Why can't I take 1 to -4? And why can't I take -3 to the fourth power? Why a cannot be 0, why a cannot be 1, and why a cannot be a negative number? Why? 0 to the third power is 0. 1 to -4 is 1 over 1 to the fourth, which is still 1. And -3 to the fourth is 81. What are you talking about? Well, if we allow the base to be this, or this, or this, we will not be able to define the log function. Okay? So that's why these are not allowed as the base of an exponential function. So the logarithmic function is the inverse of that. Log same base of x. Okay, so let's look at these graphs. The exponential function with a base greater than 1 is what we have been facing in the last 2 years. I never thought I would say this, how dangerous this function is. And when they say we're trying to flatten the curve after so many deaths in the country and everywhere else, okay? Which means if 10 people are sick today, in 2 days, 50,000 people, I'm exaggerating, 50,000 people would be sick. So that's why this is a dangerous function. It's good for other things, but when it comes to a pandemic, it's just horrible, as you've noticed. Okay, so I'm going to draw y equals x. And I'm going to reflect this graph. And the reflection of this graph is this. And this is the natural log, log base a of x for a greater than 1 in both cases. So whenever we talk about two inverse functions, not only the domain of one becomes the range of the other, and the range of the function becomes the domain of the inverse, but also their graphs are symmetric with respect to this line. They have to, see, I could have not done this on the chalkboard, right? So these have to be completely overlapping with respect to y equals x. Otherwise, they are not inverses of each other. This point moves here, this point moves here, across y equals x. Okay? So that's why these two, not only they reverse domain and range, but also have their graphs symmetric with respect to y equals x. Now, notice that this function is very nice and friendly, defined everywhere, with domain 0 to infinity. Well, the reverse happens here. Domain 0 to infinity and range everything. One more time. This has domain everything. It will be the range of this function. Range is 0 to infinity. It will be the domain of this function. And this is a vertical asymptote for this function, and this is a horizontal asymptote, of course, for this function. If this one has a horizontal, the other one will have a vertical. So this is only in the case in which the base is a number strictly greater than 1, not 0, 1, or negative. This one looks like this. It's a decreasing function on all its domain. This is still a to the x, but a is tiny, small positive, not 0, not 1. Yes, I have to draw y equals x again. And I have to draw the inverse function. Careful now. This function, or either one, did not cross y equals x, but this one does. If this one crosses at this point, so does its inverse, because all these points are the same. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So if this point is a comma b, which actually has to be a comma a, when you reverse a comma a, it's still a comma a. So now this is the function, and this is log base a of x. So this was a quick reminder of how the graphs look, because, of course, now we talk about limits. So two examples that we just talked about when the base is 10 and base is e. However, I'm not sure why, but I'll stick with the book. The book does not talk about any other base but e. Fine. So it's only base here which is greater than 1. So base base e is a number greater than 1, 2.7, blah, blah, blah. So if we want to talk about this, this is two things here. One, natural exponential function, which means base is e. So this is f of x, e to the x. And of course, the natural log function, which is the inverse of this, natural log function, which is f of x natural log x. Notice that there is no base. Here I wrote a base. By convention, ln means base e. We do not write it, but it's there. And the graphs are very similar to what we just discussed. Okay. Now, I would like us to start by looking at page 203. And just, we need to practice a few things, some properties, etc. I'm going to explain in a minute. So maybe we should review the properties of log. Okay, properties before we look at examples. Properties of the log function. The most important property that I would like to explain is that any log equation can be replaced or changed into, converted into, whatever you want to say, by an exponential equation. And vice versa. Any exponential equation can be changed into a log. Any log into an exponential, any exponential into a log. So how do we write this? Log base a of x equals y. This is equivalent to counterclockwise, and we start with the base. A to y equals x. Let's stick with natural log, because that's what this book is showing. So natural log, let's say 2x minus 1 equals 5. So we know that the base is here. We don't see it, but we know it's there. How will I change this into an exponential equation? Anyone wants to give it a shot?
Would it be e to the 5 equals 2x minus
That's it.
1?
E to the 5th equals 2x minus 1. And from here we can solve. Let's review other properties and we'll come back to examples. Thank you. Any questions, anyone? Any questions? Anyone, any questions? Stop me anytime, please. Okay, so property number 2. Log applied to a product in any base. You don't even have to write the base. Let's say this is how we write common log, right? Log log with no base. We know it's 10. This is the sum, log of x, log of y. I'm not distributing log. This is not a distributive law. So log x and log y. And I can go backwards if I need to. If I have the sum of two logs and they have the same base, then I can write this. Property number 3. So this is the product rule. Product rule. We also have the quotient rule. Anyone remembers what does it equal to? The quotient rule.
Log of x minus log of y.
Exactly the same. Thank you so much, Rachel. So this is log x minus log y. And there is one other property. So that is the power rule. So log of x raised to power b. Power rule, yes. Rule. I'm trying to write uppercase so everyone understands. And sometimes so this becomes a factor in front. By a factor, I mean it's multiplied, not addition, multiplication, or any other operation. Multiplied. Log x. There is also something, and I'm going to edit here, change of base. And this is the last one. Change of base formula. So if I have log base A of x and I want to change it into natural log, I will have natural log of x at the top over natural log of the previous base in the denominator. Notice that this has nothing to do with this. This is log applied to a quotient, and this is the quotient of two logs. Natural log of x over natural log of a. Also, maybe like a reminder, this should not be, they're not really properties, but I'm going to add them here. Natural log e and 7 natural log 1. Anyone would like to give those to us?
E will be equal to 1,
Exactly.
and 1 will be equal to 0.
Of course. How do we know? Right here. Natural log 1 is 0. Why? Because e to 0 is 1. Okay? Good. Now let's look at page 203.
Quick question.
Yes.
You showed us on the second property that, like, with the sums, if they had the same base, you could technically write it as log x times y. Is that true with like the other ones you just?
Oh
listed?
yes,
like,
of course.
Yeah,
They
okay.
go back and forth, all of them. Even this. And here, this is very easy, right? E to which power is e? 1. E to which power is 1? 0. Good, so let's